So Colin and I are both chemists and we use extreme conditions in our research. And one of the extreme conditions that we use is pressure. And so today we want to take you on a journey through pressure. And whilst we go on this journey, we're going to highlight some of the research that happens both at Edinburgh and also further afield. We've brought along with us some very special goggles as well, excellent. Some very special tercentenary balloons. So this year in the School of Chemistry at University of Edinburgh, we're celebrating 300 years of chemistry. So we've got our lovely tercentenary symbol on the front there. So Colin is going to try and burst this balloon with a single nail. Pretty easy. That was a bang, but that doesn't count as a bang, really. So we'll warn you about the big bangs. And now Colin is going to try and do the same thing, but we've brought along a bed of nails and a similar size balloon. And he's putting on his gloves. Excellent. And he's just going to try and burst this balloon. And his arm's actually shaking. So he's putting quite a lot of force down onto the balloon, and it's still not bursting.
I can't do it, Jenny.
Oh,
you beat me.
just not strong enough. But it actually makes sense, because as he's pushing that force down, it's been spread out over a much larger area. So he needs a much higher force to create the same pressure that was needed to burst the balloon. So back in 1995, there was a spaceship, Galileo, that sent an atmospheric probe to the outer atmosphere of Jupiter. It only managed to go down about 150 kilometres before it got completely crushed by the pressures. It's about 22 atmospheres. So what we're going to do here, what you can see, is we're just going to recreate what happened to this atmospheric probe as it got crushed by the pressures of Jupiter. So we've got a can of iron brew, emptied, and now we've put in a little bit of water at the bottom, and we're just heating up that water. And over on the other side we've got some cold water. So Colin's going to put the can into the cold water.
Ready?
Yeah. So what happened was that the steam pushed out the air, and then when the steam was cooled down by the cold water, it went back to water. And because there was less air in the can, the pressure inside the can was much lower than outside the can. So the can got crushed by 1 atmosphere of pressure that we're experiencing at the moment. We brought along our own piece of kit to create a vacuum for you. It's not quite as technical. Wine bottle and a wee kind of top. This is normally used to preserve wine. So we're going to create a fairly poor vacuum, but it should be good enough. So what we've got here is some marshmallows, and we're going to take the air out. We're going to reduce the pressure. So just a quick show of hands, who thinks the marshmallows are going to increase in size? Okay. And who thinks they're going to decrease in size? Alright, okay, go Colin. I hope your arm's not too sore after down on the balloon. Excellent. So can everybody see the marshmallows increase in size? Even more. And then they're all stuck together. Excellent. And then we're going to allow the air back in. Brilliant. And the pressure increases.
So the oceans, of course, are also very important. I wanted to sort of talk to you a little bit about carbon dioxide, and everybody's heard about the greenhouse effect. We're burning fossil fuels. The carbon dioxide goes into the atmosphere and creates warming of the climate. But actually, one of the things that's often forgotten is the effect of carbon dioxide on our oceans. This is a great big reservoir. Carbon dioxide dissolves in water, and we end up with something called carbonic acid. Carbonic acid then dissociates to H+, which is a source of acid. And one of the issues that we have to worry about is what sort of effect that has on our coral reefs. If you change the acidity or change the pH, then these fragile ecosystems can be destroyed. So Jenny's got here a flask of water. She's going to put in some indicators. This is good fresh Orkney water, so hopefully it should go green if the water's right. Looks pretty good to me. You just move it into the centre just so we can see it. Just hold it up against your lab coat so we can.
Is that enough? Do you want
A bit more. I can start to struggle to see these things these days. So we've got some nice, good neutral water. And it's carbon dioxide, instead of the bubbling carbon dioxide through it, we're going to cheat a little bit. We're going to throw in some solid carbon dioxide, some dry ice, which we brought up from Edinburgh. We're going to see what the effect of this is going to be. So it's at minus 78 degrees C, so colder than even on an Arctic day. It sublimes, goes straight from the solid to the gas, which is why it's called dry ice. And hopefully you can see that as you put it in the water, we can see lots of what looks like smoke coming off. It's really just carbon dioxide. And of course we also get a colour. A bit more, Jenny. Come on.
A bit more. We've carried this all the way.
I don't want to carry this stuff back to Edinburgh. That's much better. Okay, so you can see actually that water is gradually going yellow, and if we leave it long enough, it will gradually go bright pink, indicating that we've got very acidic water in that.
So we're just setting up an experiment now. So we've got a disc, a superconducting disc. We're using some liquid nitrogen, that's about minus 200 degrees Celsius, so that we can make it superconducting. And then we've also got a magnet with us, and hopefully, once it's cool enough, which it really is, we should start to push away the magnet. So this is the Meissner effect. It's better than magic. So Colin's just going to demonstrate there are no strings. Beautiful. So
I've got my own little light gas gun here. So this is a Coke bottle containing hydrogen oxygen mix, 50-50 mix. And one of the interesting things, of course, is that it's survived quite happily all the way since Thursday evening when they filmed it. So hydrogen oxygen actually is pretty unreactive, it would appear. Well, that's true to some extent, but what I've got to do is I've got to break some of these hydrogen bonds. It's actually quite a strong bond, and what I'm going to do is I'm going to break it not with a match, it's too boring. I've got a catalyst here, and this catalyst is palladium on carbon, so a small amount of palladium, and that should break the hydrogen bond, and we should get an explosion there. So this may be a little bit loud, particularly if you're at the front, so you may want to put your fingers in your ears for this one. Watch carefully, observe.